From the backyard of our own solar system to the distant shores of the cosmic ocean, the universe is full of mysteries. It has always been like that, a twilight zone of secrets, unexplained phenomena that are sure to cause shivers. And now, in the infinite blackness of space, billions of miles from Earth, something weird is happening on board one of the most iconic NASA spacecraft of the 20th century. Voyager 1, humanity's most faraway spacecraft, has come up on half a century of flight time and still going strong. Even more bizarre, there are no signs that the probe has broken or anything. Scientists from NASA are desperately trying to find the reason. So, what's happened exactly? What could this horrifying signal be? And what does it mean for us all back on Earth? Join us as we dig deep into the Voyager's grand tour thus far and the new terrifying signal in deep space that has left scientists and researchers puzzled. Launched on September 5, 1977, the one-ton Voyager 1 was meant to chart the outer solar system, in particular the gas giant planets Jupiter and Saturn's moon, Titan. Its twin, Voyager 2, launched the same year, followed a different trajectory with a slightly different mission to explore the outer planets before heading to the solar system's edge. Those were NASA's glory days. A few years earlier, NASA had successfully landed men on the moon and won the space race for the US. NASA's engineers were the envy of the world. To get to Jupiter and Saturn, both Voyagers had to traverse the asteroid belt, which is full of rocks and debris orbiting the Sun. They had to survive cosmic rays, intense radiation from Jupiter, and other perils of space. But the two spacecraft made it without a hitch. And then, the twins have embarked on a grand tour of the solar system. Their discoveries are the stuff of legend among planetary scientists, many of whom still rely on the unique images from the spacecraft's wide-angle and narrow-angle cameras. Jupiter's turbulent atmosphere, Saturn's morphing rings, the tilted axis of Uranus, and Neptune's great dark spot. Humanity had a vague understanding at best of the solar system's far-out worlds from over 40 years ago. But when the Voyager twins began their incredible multi-decade tour of the giant planets, they gave us revolutionary insights, revealing the cosmos like never before. With thousands of photographs, Voyagers 1 and 2 revealed the outer solar system in all its splendor for the very first time. Early in their travels, 4 decades ago, the Voyagers gave astonished researchers the first close-up views of the moons of Jupiter and Saturn, revealing the existence of active volcanoes and fissured ice fields on worlds astronomers had thought would be as inert and crater-pocked as our own moon. Specifically, Voyager 1 reached Jupiter in March 1979, 546 days after its launch. Voyager 2, following a different trajectory, arrived in July of that year. Both spacecraft were designed to be stable platforms for their Vidicon cameras, which used red, green, and blue filters to produce full-color images. They hardly spin at all as they speed through space. Their rotational motion is more than 15 times slower than the crawl of a clock's hour hand, minimizing the risk of blurred images. Altogether, the Voyagers took more than 33,000 photographs of Jupiter and its satellites. It felt like every image brought a new discovery. Jupiter had rings. Europa, one of Jupiter's 53 named moons, was covered with a cracked, icy crust, now estimated to be more than 60 miles thick. As the spacecraft left the Jupiter system, they got a farewell kick of 35,700 miles per hour from a gravity assist. Without it, they would not have been able to overcome the gravitational pull of the Sun and reach interstellar space. At Saturn, the Voyagers parted company. Voyager 1 hurtled through Saturn's rings, taking thousands of hits from dust grains, flew past Titan, a moon shrouded in orange smog, and then headed north, out of the plane of the planets. Voyager 2 continued alone to Uranus and Neptune. In 1986, Voyager 2 found 10 new moons around Uranus and added the planet to the growing list of ringed worlds. Just 4 days after Voyager 2's closest approach to Uranus, however, its discoveries were overshadowed when the Space Shuttle Challenger exploded shortly after launch. All 7 of Challenger's crew members were killed, including Krista McAuliffe, a high school teacher from New Hampshire who would have been the first civilian to travel into space. 3 years later, passing about 2,180 miles above Neptune's azure methane atmosphere, Voyager 2 measured the highest wind speeds of any planet in the solar system, up to 1,000 miles per hour. Neptune's largest moon, Triton, was found to be one of the coldest places in the solar system, with a surface temperature of -391 degrees Fahrenheit or -235 degrees Celsius. Ice volcanoes on the moon spewed nitrogen gas and powdery particles 5 miles into its atmosphere. Voyager 2's images of Neptune and its moons would have been the last taken by either of the spacecraft had it not been for astronomer Carl Sagan, who was a member of the mission's imaging team. With the grand tour officially completed, NASA planned to turn off the cameras on both probes. Although the mission had been extended with the hope that the Voyagers would make it to interstellar space, it had been officially renamed the Voyager Interstellar Mission. There would be no photo ops after Neptune, only the endless void and impossibly distant stars. Sagan urged NASA officials to have Voyager 1 transmit one last series of images. So, on Valentine's Day in 1990, the probe aimed its cameras back toward the inner solar system and took 60 final shots. The most haunting of them all, made famous by Sagan as the pale blue dot, captured Earth from a distance of 3.8 billion miles. It remains the most distant portrait of our planet ever taken. Veiled by wan sunlight that reflected off the camera's optics, Earth is barely visible in the image. It doesn't occupy even a full pixel. Sagan, who died in 1996, worked really hard to convince NASA that it was worth looking back at ourselves, Spilker says, and seeing just how tiny that pale blue dot was. The tenacity and commitment of astronomers like Sagan were rewarded on August 25, 2012, when Voyager 1 passed through the heliopause that marks the edge of the Sun's solar wind and entered interstellar space. In 2018, Voyager 2 did so as well. Now, the two spacecraft are chugging through the vast outer reaches of the solar system. In other words, the Voyagers were beyond astronomers' wildest dreams. But their extraordinary journeys are far from over. Now more than 15 billion miles away, Voyager 1 is the farthest human object and continues to speed away from us at approximately 38,000 miles per hour. Like an old car that continues to run, or an uncle blessed with an uncommonly long life, the robotic spacecraft is a super eager that goes on, and, in doing so, has captivated space buffs everywhere. In the blackness of space billions of miles from home, NASA's iconic spacecraft still sends signals back to Earth, delivering us new insight into some of the big mysteries of interstellar space. Both Voyagers are now so far from Earth that a one-way radio signal traveling at the speed of light takes almost 23 hours to reach Voyager 1 and just over 19 to catch up with Voyager 2. Every day they move away by another 3 to 4 light seconds. Their only link to Earth is NASA's Deep Space Network, a trio of tracking complexes spaced around the globe that enables uninterrupted communication with spacecraft as Earth rotates. As the Voyagers recede from us in space and time, their signals are becoming ever fainter. But faint as they are, those whispers have upended astronomers' expectations of what the Voyagers would find as they entered the interstellar phase of the mission. The Voyager mission's meager measurements have revealed a complex, dynamic structure produced by the interplay of our Sun's exhalations with the interstellar medium's stronger headwinds. Both first pass through a transitional heliopause boundary region, where the pressures of the solar wind and the interstellar medium are in a delicate balance. Outside the heliopause, the territory remains mostly uncharted. Sculpted by galactic magnetic fields and showers of particles from the ancient explosive deaths of massive stars, our heliosphere may most resemble a windsock, stretching out a long, undulating tail in its wake as our solar system moves through the Milky Way. Conversely, it may be more like a simple bubble or something in between these two cases, a croissant-like shape with twin tapered trailing lobes. No one yet knows. But what is certain is that the heliosphere shields us from most of the high-energy cosmic rays that fill our corner of the galaxy, rays that, striking our fragile planet, can alter the climate and even our own DNA, ripping apart the cellular machinery at the base of Earth's biosphere. So, in some sense, part of the answer to the mystery of life's emergence and endurance on one small planet around one unremarkable yellow star may be found almost inconceivably far away, out at the unknown edges of the solar system. In other words, more data from Voyager over the next few years may hold crucial information to the origins of life in the universe. But how much longer might the Voyagers last? If everything goes really well, maybe we can get the missions extended into the 2030s. It just depends on the power. That's the limiting point. But even after the Voyagers are completely muted, their journeys will continue. In another 16,700 years, Voyager 1 will pass our nearest neighboring star, Proxima Centauri, followed 3,600 years later by Voyager 2. Then they will continue to circle the galaxy for millions of years. They will still be out there, more or less intact, eons after our sun has collapsed and the heliosphere is no more, not to mention one pale blue dot. At some point in their travels, they may manage to convey a final message. It won't be transmitted by radio, and if it's received, the recipients won't be human. The message is carried on another kind of vintage technology, 2 records. Of course, they aren't your standard plastic version. These are made of copper, coated with gold, and sealed in an aluminum cover. Encoded in the grooves of the golden records, as they are called, are images and sounds meant to give some sense of the world the Voyagers came from. There are pictures of children, dolphins, dancers, and sunsets, the sounds of crickets, falling rain, and a mother kissing her child, and 90 minutes of music, including Bach's Brandenburg Concerto No. 2 and Chuck Berry's Johnny B. Good. And there is a message from Jimmy Carter, who was the U.S. president when the Voyagers were launched. We cast this message into the cosmos. We hope someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope and our determination and our goodwill in a vast and awesome universe. What's notably, the Golden Records has a very long life. By some staggering estimates, the odds of the Golden Record surviving stretches beyond not just humanity's likely extinction, but also beyond the collision of the Milky Way with the neighboring Andromeda galaxy, beyond even the extinction of most stars. That means one day, Voyager's records could lift the veil on one of the biggest cosmic mystery. In the thousands of years humanity has been contemplating the cosmos, we are the first people to know one thing for sure. The stars beyond our sun are teeming with planets. They come in many varieties, and a good chunk of them are around the size of Earth. But so far, we have no evidence of life beyond Earth. Is life in the cosmos easily begun and commonplace, or is it incredibly rare? But like most scientific questions, getting an answer to this one just breeds more questions. Which, if any, of these exoplanets harbors some form of life? How quickly does life get its start? And how long does it last? The universe's eerie silence has its own name, the Fermi paradox. Physicist Enrico Fermi famously posed the question, where is everybody? Even at slow travel speeds, the universe's billions of years of existence allow plenty of time for intelligent, technological life forms to traverse the galaxy. So, why is the cosmos so quiet? Meanwhile, exoplanet discoveries over the past 2 decades have filled in a few of the terms in the much-debated Drake equation, a chain of numbers that might one day tell us how many intelligent civilizations we can expect to find. Most of its terms remain blank: the fraction of planets with life, with intelligent life, with detectable technology. But the equation itself suggests we might one day arrive at an answer. It feels at least a little more hopeful than Fermi's silence. The Drake equation yields many interesting lessons, and when it was first put forth, it was a monumental achievement from a scientific perspective. For the first time, it broke up a seemingly unknowable question of how many intelligent, spacefaring civilizations there are within our galaxy today into a series of smaller questions that we could conceive of solving one at a time. For instance, we could measure or estimate things like the rate of star formation in the Milky Way, the share of stars that have planets, the average number of potentially life-supporting planets around stars with planets, the fraction of planets that could have life that actually wind up with life, the fraction of planets with life that go on to develop intelligent life, the fraction of intelligently inhabited planets that emit detectable signals, the length of time that such civilizations continue to emit those signals. When you multiply all of those things, you'll wind up with an estimate for the number of active civilizations that we could potentially detect today. But immediately, we run into a few major problems. For one, we've measured the rate of star formation in the Milky Way, and we actually know it pretty well. Unfortunately, if you took that star formation rate and multiplied it by the age of the universe since the hot Big Bang, you'd wind up with almost no stars. You'd calculate that the Milky Way should have formed a total of around 10 billion stars over our cosmic history. I know that 10 billion probably sounds like a big number, but compared to the actual estimate for the number of stars in our galaxy, which is more like 400 billion, it's only 2–3%. Fortunately, it's easy to identify why this method of calculating how many stars we've formed, which you'd imagine would give you the total number of stars in the galaxy, is so thoroughly wrong-headed. The superficial reason is fairly obvious. The star formation rate is not constant over our cosmic history. In fact, we've come to understand that the universe was born without stars, which began forming during the first 200 million years or so. We've learned that star formation increased for the first 3 billion years of our cosmic history, reached a peak, and has been dropping ever since. Locally, we've probably experienced bursts of star formation when we've absorbed smaller satellite galaxies, and we might even be starting to experience another burst as the Magellanic Clouds and Andromeda exert their gravitational influence on the gas, dust, and other neutral matter within our own galaxy. But that's only the superficial reason why the Drake equation is problematic today. The deeper reason is that the Drake equation, when it was put forth, made an assumption about the universe that we now know is untrue. It assumed that the universe was eternal and static in time. As we learned only a few years after Frank Drake first proposed his equation, the universe doesn't exist in a steady state, where it's unchanging in time, but rather has evolved from a hot, dense, energetic, and rapidly expanding state. A hot Big Bang that occurred over a finite duration in our cosmic past. Instead, a much more productive route is to calculate the quantities we now can speak about with some level of certainty, and then move on to the great cosmic unknowns in as responsible a fashion as we can. Unlike the situation some 60 years ago, when the Drake equation was first proposed, we now have an excellent idea of what our universe is like, both in and beyond the Milky Way and the local group. We understand what the various populations of stars are that exist, and what sorts of steps need to occur to make heavy elements, rocky planets, and allow for the possibility of complex chemistry and important reactions, such as the formation of energy-storing molecules from nothing more than the ubiquitous building blocks and starlight. We've also learned a lot about the types and abundances of planets that exist around stars other than our own, exoplanets. As recently as 30 years ago, we were only discovering our very first planets around stars besides the Sun. But now, as of July 2024, we're closing in on a whopping 5,700 confirmed exoplanets. And sure, there are biases in our data, we're preferentially detecting the planets that are the easiest to detect. But we know how to account for those biases. Instead of needing to speculate about how many stars form, how many have planets, how many planets per system have the potential for life, etc., we can actually utilize some excellent data. Here in our modern Milky Way, we already know how many stars there are, how those stars are divided into different populations, how many planets there are per star, how many of those planets have the right composition of elements to lead to complex chemistry, and how many of those planets have the potential for hosting life. On this front, it's actually straightforward to come up with a solid estimate for how many potentially habitable planets are in our galaxy. In fact, we can perform that calculation in a variety of ways just to show the power of our set of knowledge. Of the approximately 400 billion stars in the Milky Way, 80% are red dwarfs, where 18% are like the Sun, and only 1 or 2% are too massive and short-lived to be interesting for life. As far as we can tell, there are about 5 to 10 planets per stellar system, with approximately 1 to 2 planets in what we questionably call the habitable zone around each star. Of the planets that exist around Sun-like stars, we believe that less than 20% of them are Earth-like in terms of size. A greater percentage than that are terrestrial around the more common red dwarf stars. If we assume, conservatively, that red dwarf systems are not habitable at all, but Sun-like systems are, then all we have to do is multiply the following figures. The number of stars, 400 billion. The proportion that are Sun-like enough to support life, 0.18. The number of expected potentially habitable zone planets per relevant star, 1.5. The fraction of those planets that are Earth-like in size, 0.20. We then derive an estimate for the number of potentially inhabited planets in the Milky Way, 21,600,000. It doesn't make sense to use so many significant figures. 20 billion is good enough. But also we have to remember that all of these numbers have uncertainties. There may be as few as 200 billion stars, half of our estimate. Some of the stars may be too low in metals, what astronomers call the heavy elements in the universe, for planets to support life, but the percentage is small, less than 10% for certain. Some stars might not have planets, but again the percentage is small, less than 20% for certain. The habitable zone may be larger or narrower than we think. Tack another 33% uncertainty onto our estimate. And we haven't sampled the low end of the mass radius portion of the exoplanet population very well. Our estimate of 20% being Earth-like in size could go up or down, so it's reasonable to put a 25% uncertainty on that figure. All in all, there could reasonably be as few as 5 billion potentially habitable planets in the Milky Way, or perhaps as many as 50 billion. If red dwarf systems are potentially habitable as well, that number could increase tenfold. And at the same time, many of the things we've worried about in the past likely don't particularly matter one way or the other, such as whether a planet has a major moon or not, whether it has a Jupiter-like world in its stellar system, whether it's located close to or far from the galactic center, whether it's a part of a singlet or multi-star system. But beyond that, we still have some major unknowns, where our level of cosmic ignorance is truly staggering. We know the ingredients that life requires are ubiquitous everywhere we look, in asteroids, in gas in the galactic center, in outflows around massive, newly forming stars, and even in the atmospheres and on the surface of other planets and moons in our solar system. But even with all the raw ingredients, what is the fraction of potentially inhabited planets where life actually arose from non-life? In Carl Sagan's original Cosmos series, he gave a figure of 0.1, 10%, and asserted that this was a conservative number. That is not necessarily the case. Life could be difficult. Just because it arose early in the history of Earth doesn't mean that a significant fraction of planets actually have or ever had life on them. It could be nearly 100% or 10% or 1% or 0.01%, or a 1 in a million chance that life arises from non-life. If we rewound the clock and started Earth over again, how likely is it that life would have arisen and thrived here? Our ignorance is astounding. Similarly, once life does arise, how often does it get wiped out, versus how often does it endure for many billions of years? How frequently does it remain in a relatively simple state, unable to develop complexity, differentiation, multicellularity, or sexual reproduction? How often, even after billions of years, does it actually begin to look like life on Earth at the start of the Cambrian explosion? Again, we have no knowledge at all about how this might work. If you estimated that it occurred 10% of the time, that's reasonable. But so is 90% of the time. So is 0.01% of the time. Without observational or experimental evidence to point us in the right direction, we're simply deluding ourselves if we make a strong assertion. Furthermore, we know that after life on Earth became complex, differentiated, multicellular, and sexually reproductive, it still took more than 500 million years for a species to arise that would become technologically advanced, and that was likely just the result of random chance. How often does that occur? Does it make sense to represent this probability in percentages, or is this such a rare event that it's like winning the Powerball lottery 5 times in a row? Furthermore, how long does that technologically sophisticated life endure? Does it ever become a multi-planet or even an interstellar civilization? Or is the progression from technologically advanced to extinct a relatively rapid one? At this point, our uncertainties are so large that it's eminently reasonable that not only might human beings be the only intelligent life in the Milky Way, but in the entire observable universe, which likely contains more than 1 trillion times as many stars as our own galaxy. We can confidently say, give or take, that there are perhaps 20 billion Earth-sized planets made of similar elements to our own world, at the right distance from their parent star to have liquid water on their surface, assuming an Earth-like atmosphere as well. But if aliens truly exist, how can we communicate with them? Perhaps AI can help. AI mania has overtaken our economy and will soon expand beyond Earth to become omnipresent in spacecraft as well. And just like on Earth, AI promises a rethinking of long-cherished hopes for space exploration, such as finding that we are not alone in the universe. AI's advances explain this ambition. Introduced in 2017, the Transformer Neural Network architecture has become the cornerstone of today's large language models, or LLMs. Trained on internet-scale datasets, these models contain vast human knowledge and are changing our world. They will affect nearly 40% of global employment, according to the International Monetary Fund. But could this technology help us communicate with hypothetical advanced civilizations elsewhere? To be honest, this is a radical and potentially risky idea because unfriendly aliens could misuse this information. Nevertheless, it's a discussion worth starting, given recent discoveries. Space telescopes such as Kepler and the Transiting Exoplanet Survey Satellite, or TESS, have revealed that our galaxy is full of exoplanets, and it's estimated that at least 300 million are similar to Earth and potentially harbor liquid water. We believe that several of these worlds could host technological civilizations curious to meet us and learn about us. For interplanetary communication, smaller open-source language models, such as Meta's Llama 3 70B and Mistral AI's Mixtral 88Act22B, would allow for training with curated datasets. Typically, Llama 3 70B is around 130 gigabytes in size, which is a bit hefty to transmit across light years without errors. With a technique called quantization, however, we could squeeze it into a few gigabytes while maintaining its performance. Crucially, for interstellar communication, it would allow the AI to run on its own without an internet connection. Assuming we want to send these LLMs to extraterrestrials, we have 2 primary technologies: radio communication, which is broad and slow, and laser communication, which is directional and fast. By radio, NASA's Lunar Reconnaissance Orbiter achieves data transmission rates of up to 100 megabytes per second for downlink. That means it would take about half hour to transmit the entire full-size Llama 370B model to the Moon. The Lunar Laser Communications demonstration has achieved data rates of 622 megabytes per second, which would reduce the transmission time to about 5 minutes. Reaching advanced civilizations beyond the Moon involves addressing the immense distances between stars, signal attenuation, and current technological limits. For instance, NASA's Psyche mission, which launched last year toward a metal-rich asteroid, is equipped with a prototype laser interplanetary communication device. That laser technology has achieved a data rate of a few hundred Mbps. Interstellar communication with current technology would likely drop to 100 bits per second, however, resulting in a transmission time of hundreds of years to send an AI to Alpha Centauri, our nearest neighboring star system, lying a little more than 4 light-years from Earth. We could instead transmit a well-curated and smaller model, as discussed above, of only a few gigabytes in size in less than 20 years, making it a feasible project for humanity. It would not only generate text, but also images and sounds. Its content, personality, and tone should be determined by researchers, philosophers, historians, and other experts to represent humanity at large. Using more powerful lasers to increase transmission rates is another approach. By combining multiple 10-kilowatt lasers to achieve a 100-gigawatt strength transmitter, as proposed by one of the breakthrough initiatives, we could transmit large amounts of data across several light-years. Another advanced project suggests using the sun as a gravitational lens to amplify signals and create a super-fast interstellar communication system. We'd need a probe equipped with a laser at 550 astronomical units, or 82 billion kilometers, from the Sun, beyond the orbit of Pluto. Another, albeit more antiquated solution, is to equip every space mission with a simple, ruggedized onboard computer containing a well-curated LLM and an interface for communicating with it. This digital time capsule approach will both pay tribute to and naturally extend the legacy of the analog Voyager golden record. That gold-plated copper disc included carefully selected images, sounds, music, and messages intended to communicate the story of our world to extraterrestrials. In the distant future, an intelligent civilization may encounter a spacecraft equipped with an ancient computer or receive a signal containing instructions to rebuild our AIs. This indirect communication with us could reveal our past, our ambitions, and our essence as a technological species, showing these life forms that they were not alone and that a civilization of humans once existed, perhaps not so different from their own, and perhaps still around. The time has come to leverage our AI advancements for a new era of interstellar communication. By sending well-curated large language models into the cosmos, we will open the door to unprecedented exchanges with extraterrestrial intelligences, ensuring that our legacy endures, even when we might not. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.